Appreciate it. Welcome everyone. And as we go today, like I made mention, I think we just had a few folks join. You should see a chat window. If you don't, at the bottom of your screen, there's probably an icon there. So as we're going, if you don't have audio or video and are wanting to communicate with us, feel free to do so. The goal of today is to really look at the, well, bottom line, importance of algorithms, right? It's what I would consider to be the second half of coding. You know, a lot of you are either enrolled in the boot camp or are interested in doing so and are looking at that type of a career change. And as you go into that, first off, I commend your decision. That's awesome. We definitely need you in the field. But as you go through that, I want you to, in the back of your mind, begin to think about how do I master my craft? And that's really sort of the discussion today. Almost the subtitle there is mastering your craft, as far as it's not just a matter of coming up with any solution, it's coming up with the best solution. You know, there's a lot of times I'll tell my students, I said, you know, the difference between a beginning programmer and a seasoned programmer is that a beginning programmer will look for any solution, where a seasoned programmer looks for the best solution. And what's the difference between any solution and the best solution? Typically becomes part of what we call data structures and algorithms. And this focus is going to be on algorithms, on how do you solve the problem, and is that the most efficient? So that's sort of what we're going to look at. We're going to look at some demos today as we go. We'll have a little bit of fun with that. And hopefully by the end, I will have introduced you to a topic that if you're familiar with, you've at least got some more information. And if you're not familiar with, that you can begin to start putting this into your toolbox, something to be thinking about as you continue. So with that, we'll just we'll dive in here. So let's just play a simple guessing game for a moment. So I'm thinking of a number between 1 and 100, right? And so then when you guess the number, if we were to actually play, in fact, we could do this via the chat if you want, just real quickly. Let me grab a number. I always say I'm thinking of one, but I always have to actually think of one. Okay, I have one. So type into the chat pod, what is it? 23, too low, 57, too high, 34, too high, low. Okay, okay. All right, I can see where this is going. Okay. I'm actually quite amazed at the numbers that you've typed in. And the reason I say that is I wouldn't have guessed any one of those numbers. So the question then is, why did you choose those numbers? And there's a couple ways to think of this program. If you think of, if you played this game with, say, a 4-year-old nephew, even though there's only 100 numbers, they could easily take 150 guesses, because they're just going to randomly choose numbers and probably duplicate themselves at some point because they don't remember what they've asked. Whereas if you think of how could I do this most efficiently, if you're going to tell me too high and too low, the very, very first guess should have been 50. And at that moment, you will learn whether it's too high or too low, and you will have taken your sample space from 100 numbers down to 50. And then in that case, 50 would have been too high or too low. So the next guess should have been 75. Because what you're doing is you're cutting it in half. It's each time. So if you follow that, how many guesses before you actually get it? The answer is actually 7. If you take the 4-year-old approach here, where we're going to check every number randomly, worst case, assuming you don't duplicate, 100 guesses, right? Best case, you get it right out of the box. And if that's the case, let's head down to the casino. We'll play some Keno. But on average, probably around 50 guesses, usually, right? If you're just randomly choosing that, statistically that would play out. But if you started checking the midpoint, so we started with 50 and then went to 75, and you continue to cut each time you guess, you cut your data set in half, then worst case is 7 guesses. And the reason is by cutting in half, you're actually dealing with a logarithmic function or an exponential function. And it's 2 to the 7th is actually 128. So we could play this game all the way up to 128, and you would be guaranteed to get the guess in a maximum of 7 numbers. Best case, still 1. Average is actually a little above 6, because it typically you're going to get in there between 6 and 7. This cutting in half, this is the same thing that like a binary search will do. Okay, similar type of an approach. So we're going to get a little mathy for just a moment. Okay, let's talk logarithms for just a second. So if you have something log base x of y equals n, that formula, if you will, is the exact same thing as saying x raised to the n equals y. Those are the same, and we use those interchangeably a lot when we study algorithms and are trying to figure out whether or not something is logarithmic. So in mathematics, when we say log n, in mathematics, we're working in a base 10 system. So we really mean a logarithm base 10 of n. But in computer science and working with algorithms, when we say log n, we're really talking about base 2. And so just sort of notation so that you remember that. So here's the example, the guessing game, 100 numbers. What we're trying to do is we're trying to find out what is log base 2 of 100. We have 100 numbers. It's log base 2, meaning we're cutting the data set in half each and every time. So the question is, what is the maximum number of guesses? Well, then that means we just have to find where is 2 to the x greater than 100. And in this case, when we get to 7, we get to 128, because 2 to the 6th is 64. So 6, you might get it in 6 guesses, but you're not guaranteed to get the answer in 6 guesses. You are guaranteed by the 7th guess, because you will be able to have covered the entire data set. So I hope everybody was okay. A little bit of mathy, a little bit of logarithms. It may have been a few years since you've used those, but that's important for today's conversation. So let's play out a scenario. The pet moving company. Eric and Jack, I hope they're going to watch this at some point. Eric and Jack diversified the Tech Academy into a new niche market, pet moving. They saw the need for assisting families being relocated. Their research shows that families, on average, have about 2 pets. Typically, a couple cats or a couple dogs, an occasional hamster, small reptile. So here's the question for you. How would you price such a service? If you were actually doing this, how would you price it? Would it just be a flat rate times how many pets? I don't know about you, but moving a small reptile in a box is probably a lot easier than some large dog, right? So I'm guessing you probably would have a price based on maybe size. Does that make sense? I'm hoping. If that's the case, play this out with me. How much for this pet? I don't know, $5, 10, something simple, right? Easy. How much for that pet, right? This now totally changes the picture, doesn't it? The size alone, we're talking about an elephant, completely overrides anything we were just talking about with a goldfish. So at the end of the day, the workload and the cost can really be calculated. If we look at what's the cost of moving a goldfish and an elephant, well, it's really just the cost of moving the elephant, because the goldfish doesn't matter at that point. And that actually is algorithm analysis. What we're looking at is we're looking at what takes the largest amount of time and processing and operations. And you sort of hand wave away the things that really just don't matter. All right. So I always tell my ground students, think of elephant and goldfish when you're evaluating what's called big O. And big O notation is where you evaluate an algorithm to some sort of a classification. Okay. So let's look at a couple examples of this. All right. How's everybody doing, first of all? This is really weird because when I'm in the Tech Academy face-to-face, it's much more interactive, right? Pretty good. All right, thank you, Linda. Appreciate it. All right, so here we go. Elephant, goldfish. Here's some big O examples. When we look at these, think of N in these mathematical functions as the amount of data that we have to process. And the functions that we've written represent the number of operations that have to be done. So let's take this first one. N plus 8. Well, if N is 2, then that 8 has a huge impact, doesn't it? Because instead of 2 pieces of data, we have 10 operations, right? It's 500% increase over the number of pieces of data. But if N is 100, well, then the 8 sort of has a little bit of impact, but not much. What if N is 1,000,000? 8 doesn't even matter anymore, right? So the elephant in this is the N. The goldfish is the 8. So we would write this as big O of N. That function would have a big O analysis of order N, meaning that if you have 1,000,000 elements, you have roughly 1,000,000 operations. If you have 500 elements, you have roughly 500 operations. So it's a linear function that is directly proportional to the amount of data that you're putting into it. Let's look at the next one. Let's say we have something that's n squared minus 3n plus 100 that evaluates out to that, whatever it may be. Well, if n is 10, well then I have 100 minus 30 is 70 plus another 100. I have 170 at that point. The 100 at the end and the 3n, they actually have a pretty big impact. But what if n gets very, very large? What if n is 1,000,000, right? 1,000,000 squared is a really large number. Minus 3,000,000, yeah, that doesn't really even matter much at that point. Plus 100, that's nothing. So in this case, the n squared is what's driving this particular algorithm. That's where the elephant is. The goldfish is really just the minus 3n plus 100. You know, you have to think about as n gets very, very large, what does this function do? What parts of this function really take over, all right? And in this case, say the n squared takes over. Right? The last one, I have a function that no matter what I put in for n, the answer is always 1. So if I give it 2 pieces of information, there's 1 operation. If I give it 1,000,000 pieces of information, the operation is 1. In this case, there is no elephant. It's only a goldfish because you're coming out with a constant. Do these examples make sense to you? What I'm trying to show here as far as when you look at this mathematically, you really are looking at what drives the end value. And in this case, it definitely is the n squared. All right, thank you very much, Jesse and Frank. So here's the main classifications of algorithms. I know it's probably really small to read for you guys, and I apologize. I need to redo this. I need to do this graph myself. I found this, I've been using it for years, but think of it this way. Along the horizontal axes is the number of elements, or think of that as the size of your data. Along the vertical axes is the operations. Think of that as the amount of processing that has to take place in order to complete the task. Well, if you have any, if you have any algorithm that's down here along this flat line, along the horizontal, or even that green line that is slowly rising, and to some degree, even this purple one that's right in the middle, if you have algorithms that evaluate there, your software is going to be pretty quick. In fact, if they're on the bottom, it's almost going to be instantaneous for the user. If you're working with large sets of data, it's just, there's the answer. It's right there. You know, the purple, they may have to wait just a second or two, but then it's right there. If you have algorithms that you write that end up being in these 3 that are going skyward, typically the user will quit the software and stop the process and not let it finish because they've waited too long, because it takes way too long to complete. So we're always striving for algorithms that have a much better efficiency. Now, are algorithms of every single one of these categories, are they solutions? Absolutely, but they're not all good solutions, right? Some of them can be quite bad. All right, well, let's look at a couple other brain teasers, and then we're gonna actually look at something I coded up to take a look at. So the first thing, how about this? Let's say I have 8 identical looking coins, but one of them is fake and weighs slightly less. What is the minimum number of weighings I must make to guarantee that I found the fake coin, right? So think about that for a moment. How would you do that? If you had a scale like this that was a comparison scale, how many different times would you have to weigh coins to find out if it's a fake, right? So this is a question, right? What did you guys come up with a minimum? And can you come up with an n solution? Can you come up with a log 2 n solution, log base 2 of n? So that's a question to you. Okay, Frank, that is the absolute minimum, and that is actually neither of the log base n or an n solution, but that is an absolute minimum. Nicely done. To which there might be others going, 2? Wait a minute. How do you get 2, right? I'll circle back around and we'll talk about the two, but let's look at, can we solve this using an N solution? An N solution means that I need to solve this problem by making roughly 8 weighings. Now I say roughly because if it's N minus 1, I'm going to go back here for just a minute. What would N minus 1 end up being? Well, the N would be the elephant, the minus 1 would be the goldfish, it would be an N. The reason I bring that up is because you can do this in 7 weighings, right? I got 8 coins. I take the first coin and weigh it against the second. First coin weighed against the third. First coin weighed against the fourth. First coin weighed against the fifth, right? And you could continue going through that and weigh essentially the first coin against all other coins. Would that work? Yes. That is an N-based algorithm. Works great for 8 coins, but if I gave you 80 coins, now it's like, oh, really? I have to do this one at a time, right? It's not the most efficient. What about a log N solution? Anybody come up with that one? Now, if you have 8 coins, how many weighings would you need to do? You would need to do 3 weighings, right? Because 2 cubed is 8. So can you come up with a solution where you have to do, to guarantee you have found that you would have to do 3 weighings? One way to do that is to take those 8 coins, and if you could split them out 4 and 4, right? Cut them in half, and then if one of the whichever one is lighter, we take those 4 and you split them 2 and 2, and you weigh it for a second time. Whichever one is lighter, you take those 2, split them one more time. That would be a log-based solution. Far more efficient than the N solution, right? Far more, because if you had 100 coins, that means the N solution, you got 99 weighings. The log-based solution, you have 7 weighings. We just did it with the guessing game. But in this situation, there's actually a much more efficient way, and that's what Frank came up with 2. And the way you do that is you leave some of the coins out. What if you weighed 3 coins on one scale, 3 coins on the other, and you leave 2 aside? Now, obviously, if the things you've weighed are even, you take the 2 coins that you put aside, 1 on each, and you found it. If either of the 3 that you put on there is lighter, you take those 3 coins, leave one of them off, weigh 2 of them. And if they're equal, the one you left off is the lightest. Otherwise, you'd find the lightest. So we just went through a number of different solutions to one relatively trivial problem. And you can quickly see how by choosing the right algorithm, you can scale the problem and still be able to solve it, right? If one of you came up with the N solution, one of you came up with the log N solution, right? At that point, if I come along, say, okay, we got 1,000 coins, well, the person who's doing the N's like, oh, I'm out. I'm done. I'm not going to find it, right? Where the other one's like, yeah, no problem. 10 weighings, right? All right. How would that change if I went to 9 coins? How would that problem change I went to 9. How many wanes do you need to guarantee? So let's start there. Think about it. Type in what you think you found. All right, we got a couple of 3s. Yep, yep, absolutely. Joe and Frank and me, correct. 3 is correct. What algorithm analysis would that be? In other words, what category would that be? Might be a little bit tricky question. It is a logarithmic. The guessing game, remember, was log base 2 because you split the data set in half each time you did it. This is actually a log base 3 because you're splitting your data set in thirds each time. And so anyway, just thought you might be interested there. All right. Well, let's get to some code and let's run some programs and let's drop my computer to its knees. So let's do some anagrams. My grandfather, this was one of his favorite games. He loved playing anagrams. And anyway, in this version, if an anagram, for those who maybe don't know, if you have 2 strings and they have all the exact same characters, I said letters, I probably should have said characters there, like Python and Tython, those are anagrams of each other, right? Because they're made from the exact same letters. So take a moment and think about this. How would you solve that? If I gave you the word Python and the word Tython, how would you solve that? And if anybody wants to type in a quick, not a massive paragraph, but if you can real high level, here's how I would do it, step, quick little note. I'm just curious. I've actually coded this up using 4 different classifications of algorithms. And we're going to go through and run it. And you're going to get to see how different algorithms react based upon the classification. All right. So if you want to tell you what, if you want to unmute yourself and jump in, tell me how you'd solve it. Go for it. Bueller.
What it would be logarithmic, wouldn't it?
Can be.
Yeah, split it in half, and solve it. But
when you say split in half, help me out here a little bit.
yeah,
Take the words Python and Tython. You got to compare these things and tell me whether they use that. So I'm not sure where the split in half comes.
Never mind. I'm quiet now.
No, I love it. Anyone else want to give it a shot? Anything comes to mind?
Would you split Python into PYT and HON and then split Tython into TYP and HON and then compare the first 2?
Oh, yeah. I see. You're almost creating sort of a recursive solution there where
so split it into 2 smaller pieces of data and then analyze those pieces.
And then recursively call that, and eventually get down to maybe a single character. That's a possibility. I did not code it up that way. One of my 4.
Okay.
So that's an interesting solution. Catherine, I like where you're going here. Create a list of characters and then look through the list in a loop. Okay, so if we took Python and Typhon, there's your list of characters. Python has 6, Typhon has 6, and just consider that a list, right? And then are you talking about when you say look through a loop, usually, actually, instead of ask you, I'm gonna just sort of continue on. Most folks will look at this and think of a nested loop. In other words, if I took every letter out of Python, so for each letter in Python, for each letter in Typhon, compare. So it's sort of like taking the P in Python and comparing it to T, Y, P, H, O, N. Then take the Y of Python and comparing it to T, Y, P, H, O, N. You guys follow? Another way, a really easy way to think of nested looping, a nested for loop, is think of, I tell my students, when there's a winter formal coming up, and let's say I have 5 guys and 6 gals, I say, what's the total number of male-female date combinations for this dance? And they're like, well, for each guy, I can match to each girl, then go to the second guy and match for each girl, and then go to the third guy and match for each girl. That's a nested loop. That's a common way to do that. That is also an n squared algorithm, which if we go back here, that would be the third line from the left. That would be the cyan color here, whatever this one is. This is n squared. So probably is not going to handle things too well as it scales. All right, let's play with it. Let's play with this. Okay, here you go. Demo discussed it. That's what we're doing now. All right, so I need to share this screen. Whoa, 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 whoa. Share. I almost hit end meeting. Okay, so I'm sitting here. I just, yeah, it's just the files I'm working with. So I have a program called Anagram. It's Python. Python 3 program. Let's go ahead and run it. Do I want to use standard in? Yes, let's use standard in. All right, first word. Python. Second word. I even forgot what I had. Doesn't even matter. Oh, I did Typhon. Typhon. All right. Now I have 4 solutions we're going to look at, and I'm not telling you which is which. You guys you can think about it. So use those 2 words and use solution number 1. Okay, it did it. Those are anagrams, and there's the amount of time it took in seconds. Okay, pretty darn fast. Let's check solution number 2. All right, faster. Quite a bit faster, 4 times faster. So let's look at number 3. Looks like faster than the first one. Look at number 4. A little bit slower, but we're talking about what we got, tens, hundreds of, tens of thousands of a second. Still pretty darn fast, right? So at this point, we could say, well, we have 4 great solutions. Well, we do have 4 great solutions for 6-letter strings, okay? Sorry, you guys, I'm getting some feedback here. Sorry about that. That was probably a lovely video. Okay, let's exit with these inputs. Let's try something else. I'm not done with the simulation. Standard in, yes. Okay, how about this? How about this word? Let's go with super duper. What do we got there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 letters. And we'll go with duper super. Okay, see what happens. Solution 1, still pretty screaming fast. Solution 2, almost the same. Solution 3, well, now that one is actually slower this time. Solution 4, over a second. And the others are still down at the 10/1000ths of a second. So that's a pretty large magnitude, right? Let's try something else here. So let's try some other inputs. You guys figured out which one's best yet? They're sort of all over, aren't they? It's not consistent yet. Well, you're starting to see that number 4 is probably really going to suck. But let's see what we got here. Oh, I ended it. All right, let's go back in. Standard in. How about this? I'm going to use the keyboard and just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I just went down my keyboard there, 12 characters. And now I'll just go the other way. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those are acronym or anagrams. Okay, number 1. Okay, a little bit slower. 2, very fast. 3, a little bit slower. 4. So anyway, what we should probably talk about here for a while is, here's a great example. If my test cases, I just ran a couple small test cases and saw that I got the right result on both of them, then I'd be like, well, all of these work. Or in this case, if I had coded number 4, and that's the one I put into production, and I quickly tested it with words like mom, dad, level. Okay, those are also palindromes, but you know, Brent, Wilson, you know, something small. If I was using, you know, it's just sort of common first names, it would appear to work extremely well. Ladies and gentlemen, my machine is still working on this problem using this algorithm. All right, so it does finish, and we are going to wait for it. So we're going to hang out. I'm missing the chat window. I lost that. I mean, where did the chat window go? Okay, my machine is, there we go. John, the goal is that there will be posted. I am recording it. We're going to figure out how we can get it all posted. Frank, I just saw your suggestion, sort and compare. That is an excellent way to go about it. And by the way, that's how you get your logarithmic algorithm. And I will tell you that one of these 4 is using that, that algorithm. Okay, this should be getting close to done. Hang in there. So here's a question to you. When you guys test your work, do you test it on small size data only? Do you try to test boundary and edge cases along with normal stuff? 154 seconds is what that took. And the others are still down in the 10 thousandths of a second. We won't be using number 4 for any of the remaining examples. So let's have some other fun with this. How about this? Exit, and we'll say we're done for a minute. I'm going to give it the following. I have Dr. Seuss's Green Eggs and Ham. And I have 2 versions of it where I've intermixed some of the words. Let's see how these do. We will not be using number 4 because we don't have enough time in this chat or today to have that finish, right? So, so if we come along and so standard in, no, we're going to use some files. Green eggs, use that text file, and we're also going to use green eggs 2. So these are anagrams, but they're scrambled. No pun intended. I just caught that. All right. So solution 1, 1.3 seconds. Solution 2, that's still pretty fast. Holy smokes, take a look at that, folks. So tenths, hundredths, we're down to a millisecond, 2 milliseconds to complete. And number 3 is down to 1.2 milliseconds. And if I did number 4, we're talking about many days to complete, not hours, days. All right. Let's do one more. And for this one, I'm not sure that I'm going to actually do, I have to look here. I ran it earlier. I don't think I have enough time to run it tonight or today. Yeah, I'm not going to. We're not going to use number 1 because number 1 is going to tank immensely on this next one as well. We'll still do number 2 and number 3. Okay. The next one I have, I'll say I've quit the simulation. Take a look, if you will, at the files I'm working with, at the file sizes. I used green eggs and ham, which was 3.3 kilobytes. So there's roughly 3,000 characters in green eggs and ham. So remember how we did it with 12? We just did it with 3,000, okay? Now, I'm gonna use this. This is a 5.2 megabyte text file. That means there's over 5 million characters in this file. And there should be. It's called William because it is the entire works of William Shakespeare in a text file. Okay? And let's see here. Catherine, you could do that, but you have to build the dictionary, right? You'd have to build the dictionary and then and for each character, not because we're looking at characters, not just words. Let's see here. No standard in William.txt and William2.txt. All right. I will not do number 1. Here's number 2. Less than 3 seconds to do that. And just so you know, the entire works of William Shakespeare have over 5.3 million characters. And it did it in 3 seconds. Number 3. just over 2. So all of a sudden, number 3 is coming out as the top candidate here because of scale. By the way, if we ran number 4 on this, there's not enough time in my lifetime or your lifetime to actually have it finish. All right. So what does that teach us? Let's go back over here to my other, finish up here real quick. Where's PowerPoint and share? All right. So what does that tell us? Well, let's look at the different solutions. Solution 1 was the n-squared algorithm. By the way, I will also make this PowerPoint set of slides available. Rick, I guess I'll be sending that to you, and you can make them available to those who are here or would like them.
I can do that.
No problem. Thank you. So this is that nested for loop. It's basically a for each letter compare. And so what you have to do is you have to walk through the first string, which would be n. There's n characters. And for each one of those letters, you have to walk through each character of the second string. And that's why you would get n times n. This is an n-squared algorithm. So this one ended up being the third, or if we rank them from best to worst, this is in third place, okay? Solution 2, this was brought up earlier, and I've lost my chat again. What is the deal with that? Oh, there we go. Who had brought that up a moment ago? Oh, the sort and compare. Frank did. This one is if you took both lists and sorted them, and now you do literally a character, just you walk the list, and you're just look at the first characters together, the second characters, the third characters, and you keep going. And if you don't find any that are not the same, then it's an anagram. And the reason this ends up being an n log n algorithm, n times the log n, is because when you sort the lists, to sort, the sorting cost is n log n by using what's called the quick sort. And so you have to do it twice because you have 2 lists. So that's where you get 2 times that. And then the plus n, which is the goldfish here, is that you have to walk the list one more time doing the comparisons of each letter. So this ends up being an n log n. This actually is the, this ends up being the second best algorithm. The best algorithm is of order n. Can you do the problem by just walking the list? And you can. Think of us setting up an array or a list of 26 positions, 26 numbers, and each number represents A through Z. This almost gets back to what Catherine was talking about counting it. All right. And as you go through each one, you literally just keep a frequency of how many times you saw that letter. When you get done walking the list, which means the 2 times n here, you had to walk the first list, you had to walk the second list. That's where you get the 2n. Then you have 26 comparisons to do because you have to compare A through Z's to make sure that those are all the same. Well, the 26 is a goldfish. The 2 times n is a goldfish. At the end of the day, the elephant here is n. And this was number 3. So the best algorithm ended up being number 3. Now let's look at what in the world did I do on number 4. All right. Number 4 is a factorial algorithm. It's horrible. A factorial means, if you say 4 factorial, that really means 4 times 3 times 2 times 1, which is 24. So factorials come into play when you do permutations on strings. So if we take our Corvette example from the beginning, and I do the permutations, all permutations on the word Corvette, and here's just a small number of them, there's over 40,320. And so this algorithm literally just says, make a permutation. Is that the answer? Nope. Make another permutation. Is that the answer? Nope. Make another permutation. Is that the answer? And it continues to do this. So for the word Corvette, this would actually work pretty decently. You'd still have to wait a while, but not like we did 12 letters, remember, or 11, and we had to wait 154 seconds. So this is absolutely the worst. Now, is it a solution for small data? 100%, but it does not scale. And that's the problem if you don't choose good algorithms. So here's a summary of all of these. And this is used with, oh, I forgot to run the abstract. The abstract here, I actually had that. That was the description of this talk that was sent out. There's 509 characters in that little description. And here's an example. If you used an N algorithm, all right, if you're able to use an N-based algorithm to solve this problem, then obviously 509 characters, 3,000 plus characters, 5.3 million characters. The second it gets to N log N, with that many characters, in the abstract, you're up to about 4,500 operations. Green, eggs, and ham, you're up to almost 39,000. And William Shakespeare, you're up to over 117 million, which, if you remember, it was able to do very quickly. Still did it pretty darn quickly, just over a couple seconds, which was amazing. If you have an N squared algorithm, take a look at this. An N squared algorithm for, oh, come on, Wilson, I am not hitting the mouse button right. There we go. Let's just use the mouse instead of the trackpad. All right, anyway, you have, if the abstract jumps up to 250,000, right? Green, eggs, and ham, N squared went to 10 million. And this is why we did not do N squared in William Shakespeare, is it took us up to 28 quadrillion operations that would have to be done on an N squared. A factorial, I didn't give you the number, but I told you how many digits were in the number. Just the 509 characters, you would actually have a number that has over 1,000 digits in it. That's how many operations would have to be done. And green, eggs, and ham would take you up to a number that had almost 10,000. And William, I don't even know. I just put the end of time as we know it. The machine would still be running by the time the Earth was no longer in existence. Okay. No question, ladies and gentlemen, algorithms matter. Coding is good, but without thinking about trying to come up with the best solution, algorithms can completely tank what you're trying to do, right? How many times have all of you been using some sort of software product and you're waiting far longer than you should have? Chances are the programmer didn't choose a good data structure or chose a poor algorithm for implementation. So with that, I'm going to just open it up. If there's any questions or comments, I hope that made sense. I tried to keep it at a high enough level. So if you're just beginning your programming experience, that it made sense. Elephant, goldfish, ladies and gentlemen, elephant, goldfish. Silence.
Well, that's good, right?
Yeah, it was very good.
Well, thank you, you guys.
Well, Dr. Wilson, what would you, I know there's a lot of good books for algorithms out. Do you have any online references that you use to find good algorithms?
You know, there's, depending on what you're trying to achieve, right? Probably the first thing is taking a look at doing sorts and working with sorting information. That's really where algorithms come into play, especially for those that are just sort of beginning, well, even advanced folks. We constantly needing to sort data. And so looking at various different types of algorithms for that. There's a lot of online resources for that. I don't know about any good books per se. There is sort of the Bible of algorithms, but I'll tell you, if you're at the beginning of your career or the beginning right now of learning this in the boot camp, don't go read this book because you'll run away screaming. I tell you, it's intense. So it's a book. The author's name is Comer, C-O-M-E-R, and I think it is called Analysis of Algorithms. It probably runs a couple $100 on Amazon, if I'm not mistaken. But it is essentially the Bible of algorithms. It's not something to, it's not light reading. It's not something that just on a sunny afternoon you want to sit down and read a few pages. So
I'll buy it, put it on my shelf for later.
now, if you're having trouble sleeping, it could be excellent.
All righty.
All right. Well, I really appreciate folks allowing me to do this virtually. I've done these for quite a few years actually at the Tech Academy on site, but never virtually. So appreciate that given the current situation we're in. So Jesse, a good point for entry point for beginners. Right now, if you're truly a beginner, the best point is you really are coding. I almost hate saying this. You got to focus on coding over algorithms as a beginner. But as you get more and more comfortable with your skills, you're going to start to think about, how could I do this differently? How could I do this better? All right. That's when it comes into play. My beginning students, I never walk in and nail them with this at the beginning. I mean, it's a couple months before I even bring this type of stuff up to them. For them, I want them finding any solution, because then they get success and they start to work through that. Once they start getting more comfortable, then you can look at the solutions and go, so why is this not real good? And we can talk about it, things like that.
I would say a good point that it really comes with experience.
Absolutely.
Yeah.
This is 100%. That's why for this presentation, I really went with the goldfish elephant, because I really wanted high level to understand the concepts. And then as you get your experience, you start thinking about, okay, I'm sitting here, I just wrote something that uses 3 nested loops. Oh, that's an n-cubed algorithm. Is that really what I want here? And you start to think of it that way.
Yeah, and we do touch on sorting algorithms. That's kind of the main thing through our program.
Absolutely, as it should be. So good. All right.
All right.
Well, with that, nothing. Okay, so with that, I'm gonna stop the sharing, and I'm gonna go ahead and hit stop the recording. And Rick, I'll let you know what happens.